Okay, so we are studying resisted motion, right? Resisted motion. Okay. The thing about resisted motion that kind of makes it special, compared to the usual, compared to the usual three in a motion, right? Is that we try to get closer to reality compared to before. Okay, we're using the same old calculus that we did before, but applying it to a wider variety of questions to just flex on our calculus skills and try to improve our mathematical reasoning skills as well, along with our calculus. If I have just a cannon, right? Just my usual cannon, again, it's shooting my ball, right? According to 3 in the maths, right, in a projectile motion, it follows an exact parabola. In reality, it doesn't exactly do that. Yeah. There are things like resistances and like air resistance, because this ball is pushing air out of its way. The air is going to slow the ball down. In reality, the ball's projectile motion would be something along the lines of that. Yeah. So now to try to get closer to reality, we need this resisted motion, right? And we're using our calculus skills to work on this. Yeah. Now, as a simple example, say for example, if I had please work. Why is this pen not working? This is dodgy. Okay. Say if I have a bucket, right, full of water. Okay, and if I have a stone, right, this stone, okay, has mass. This stone has mass m, yeah, and it's being dropped into the water, yeah. Now I want to figure out how long it will take for it to fall into the bottom. Okay, say for example this drum or bucket, whatever, is 2 meters long. That's one hell of a bucket. And this stone, right, has a mass m. Okay. Now this liquid that I have, I'm guessing it's water, for example, and I might think a little, right? This water is gonna have some resistance to this ball. So I have my ball, and I'm thinking about all the forces that's acting on this ball. There's gonna be gravity, which is mg. Remember, F is equal to ma, and this is Newton's second law. Newton second law. Yeah, we're gonna use this law specifically quite a lot in resisted motion, in general, actually. Yeah. So by using this, near the surface of the Earth, right, the acceleration due to gravity is given by a constant g. Yeah. So F is equal to mg, right? And that's the force of gravity near the surface of the Earth, right? And it's going to be like roughly 9.8, you know the number, okay? And so that's the force that gravity is pulling on this stone downwards, okay? But there's also going to be the resistance. It's going to resist its motion. That's why it's called resisted motion. To resist the motion, the force has to be acting in the opposite direction. Opposite direction, okay? And now, I might just think, as the scientist I am now, right, or the mathematician I am, okay, that this resisted force, right, this is a resistance force, okay, and it's going to be proportional, that's the scientific thing, okay, to maybe its mass times its velocity, okay? Maybe the faster that this ball is moving, the more that the water tries to resist it. It tries to slow it down. Yeah. Okay. So then I have this is a proportionality, right? This is like a ratio, right? So yeah. Then what I can say is that my resistance would be some proportionality constant, right? That's just some constant times mv, right? It's proportional to one another. If I double r, I double this mv. This k is not gonna change. It's not gonna alter in any way. That's what this proportionality means. If I double either m or v, then I double r. If I double r, I double either or both, or the product of m and v. Okay, that's how this works. Okay, about this, so then I can call this kmv as my resisted force, right? So then my total force, I would call it the sum. This is a sigma sum of all my forces. Okay, now physics really doesn't care which way I put up and down. Yeah, I can set down as positive or up as positive. The stone is still gonna move downwards. Yeah, the same effect is gonna happen, and the stone is still gonna travel to the bottom at the same time as any other way, right? What this shows is that I can choose whichever way is positive, okay, and my calculation should run just as fine, right? I'm going to say, for the sake of my argument, that downwards is positive, right? Okay, if I let downwards be positive, that means my sum of forces, right, is mg minus mkv. Just rearrange those. Again, this is a negative force because it's opposite the direction that we deemed as positive. Yeah, if downwards is positive, upwards has to be negative. Okay, now this is my total force, right? Now we can apply our good old guy Newton, right? And we can say that this is m times the total acceleration of the ball, or the rocket, or whatever. I mean, not the rocket, the stone. Sorry, I forgot that guy. So now, a here is my total acceleration. What I am seeing the ball accelerate. What, like, imagine if this is like a glass bucket, yeah, and how fast I am measuring its acceleration, if I can, yeah. And so this is a is equal is equal to mg minus mkv. Okay, this is just some equation. Now we can cancel out the m, so the mass of the stone isn't relevant at all. This is just a specific example in terms of this equations. There are other formulas for resistance applying different ideas in different fluids. Okay, but in this case, I am just assuming that my resistance is proportional to mv. Yeah. In other cases, it wouldn't be as such. It could be different values. Okay. So in this way, I have a is equal to g minus kv. Okay. A is just my x double dot, if I want to call it that. Okay, is equal to g minus kv. Okay. Now I want to see. I want to relate two things. I want to see, on one side, my velocity, and on the other, I want time. I want to see, at a given amount of time, how fast my stone is moving. That's my key question for this video. Yeah. For a given moment in time, how fast is stone? Okay, and what I'm going to say is when time equals 0, so when we just start, okay, this object is going to be on the surface, okay, and it has no velocity. Okay, so it's just going to be like, I just let it go on the surface, and it's just going to slowly drift to the bottom. Okay, and these forces are still acting on it. Okay, now, so I'm just saying when t is equal to 0, and v is equal to 0, this is just a key piece of information that we're going to apply later on. Okay, now, what I can do is I can apply my good old 4 formulas of acceleration, right? And we can plug these in, just as we did in 3net, which is going to ramp it up, and just go along with it. Okay, now we want to relate t and v, right? For a given time, how fast is it? So you want to relate time and velocity. Now, which of the 4 formulas that we can use to relate acceleration, velocity, and time? Well, we have v and t's in all of them, okay? But we want a v and a t in that specific equation, and so we're looking at something like this. This way we can relate velocity and time much more efficiently. Okay, so say now I have dv dt is equal to g minus kv. Okay, now I can't integrate as is, because if I integrate it as it is now, then my dt will come across, and I'm integrating in respect to time. I can't really do that. This entire thing is in respect to velocity. That doesn't work. So what I can do is I can flip both sides. Flip both sides. Okay, this looks like it's not a fraction, but it's actually secretly over 1, because everything is secretly over 1. So dt on dv is equal to 1 on g minus kv. Okay, now what can I do with this? Now I can integrate. So now I have t is equal to the integral of 1 on g minus kv dv, and I can integrate this. This gets me, okay, what I can do is I can take a substitution for our example. Let u equal to g minus kv. Du dv, that is minus k. So du on minus k is equal to dv. Just sub in. Okay, this minus k is on the denominator. That's just 1 on minus k. This 1 on minus k can come out of the integral. So I might be doing a few steps at once. Okay, that's just minus 1 on k, right? That's from this dv. This dv is equal to du on minus k, right? So then I'm just taking that out of the entire integral because k is a constant, remember. That's the integral of 1 on u. Remember, u is that denominator bit. Okay, and I have that du left. Okay, this is nice and easy to solve. 1 on k, natural log of u plus c. Now this plus c is gonna be a prick to me. I need to solve for that, right? Now I can use my initial conditions, right? But I can't do it as u as is. I need to sub back in because this is an indefinite integral. 1 on k, right? Natural log of g minus kv plus some constant. Okay, now this is like a sidebar, an aside. Yeah. Okay, now when t is equal to 0, v is equal to 0, right? So that means, okay, I'm just shifting over here. 0 is equal to minus 1 on k, natural log of g minus k groups of 0 plus c. That's just minus 1 on k, natural log of g. Yeah, same thing, plus c, because g is a positive constant, so it doesn't really matter if it's absolute value or not. Anyway, I have, so c would be then equal to 1 on k, natural log of g. That's just some number. Yeah, this is just some constant, this is some number. Okay, now that means my t would be equal to minus 1 on k, natural log of this one, g minus kv, plus, now this is my constant. This constant I already solved for, so that's 1 on k, natural log of g. Yeah, now I can factor out this 1 on k. That's just 1 on k, right? I can have the log of, not LG, it's not a brand, ln of g minus ln of g minus kv. Yeah, now I have this guy. Now when I'm subtracting two logs, I can, you know, deal with them at like so. I can have 1 on k, natural log of g on g minus kv. Okay, now I wanted for a given time, how fast is the stone? So from here already, I can just sub in a certain time and then solve for v. But you know, I'm a 4-unit kid, right? And I want this v as the subject of the equation because I want to flex on those other math students. Just messing. So I have kt is equal to natural log of g on g minus kv, right? Now, what I can do is I can actually take the negative of both sides. This is just a neat, nifty trick. I can say kt is equal to negative log of g on g minus kv. Why I want to do this is this negative, right? It can come inside. Now, if you take a negative, like a coefficient of a log, like the Clog law, you know, when that comes in, you raise it by that power. When you raise this by a negative power, it flips the fraction. So then you have log of g minus kv on g. Okay, now this is better for me because I have the v on the top, right? If v is on the bottom, then it kind of just gets more annoying. So then now I have e to the minus kt is equal to g minus kv on G. Now this G can come across, right? And I'll end up with GE minus KT is equal to G minus KV. Okay. Now this minus KV I can add to this side, and this hunk of junk I can bring it inside the other side, you know. So I'm adding KV on both sides, and I'm subtracting GE to the minus KT on both sides as well. So I get KV is equal to G minus this thingamabob, GE minus KT. Okay, so V is, okay, wait, how about I'll factor this because this looks nice and easy to factorize. G1 minus E to the negative KT. Now, this gets me V is equal to G on K, 1 minus E to the negative KT. Okay, now, so for a given time, I can plug this in, okay, if I know what K is, and I already know what G is, right, I can literally plug this in into a calculator, and it will spit out what my velocity is at a given moment in time. And this is like the basis of how resisted motion works. You start off with your forces, you draw a diagram, all your forces, you apply Newton's second law, or you can sub in the mass of the object if they have provided to you. They'll probably give you an indicator of how resistance is related to the object's velocity, I'm guessing. Usually it's by the velocity. If sometimes they add in the mass, sometimes they don't. But from there, then you just apply your calculus, your integration and your differentiation, and you solve for an equation of different terms in regards to one another.